Are you able to see the screen?
Yes, sir.
Okay. So any doubt regarding the phasor diagram? How to draw a phasor diagram for transformer? Do you want me to explain more once more?
Yes.
Yes, sir.
Okay. Okay, so let me draw it parallelly like the way it is done. I'll leave this UPF load for you. Let me draw for the lagging and leading PF load. Okay, so for that, how will do we start? Okay, just let me add one slide. Okay, so it is phasor diagram with lagging load. Actually, whenever I try to draw in PPT, it is creating problem. Let me explain and then draw in whiteboard. So this is what is happening when you uh, have a lagging PF load. So this is your V2 which you get from your secondary, or yes, secondary means whether you want it in a high voltage side or low voltage side depends on you which appliance you are connecting with the transformer. So secondary, primary side you are energizing, secondary side you are getting this V2 voltage and you are getting this I2 current lagging. Then V2 plus JZ2 will give you the E2, which is the induced EMF in the secondary. So V2 plus this, then J into X2, this is because of the leakage reactance, and then this is ultimately your E2. And E2 and E1 will be in phase and they'll be in some ratio. E1 and E2, that ratio should be same as the turns ratio. Then you have E1 here, just minus E1, 180 degree out of phase, and this is your phi. Let me check whether it is opened or not. Still opening.
Sir, there one thing I have to ask. Sir,
Hmm.
how are you determining the position of V2 with respect to E2?
V2
Yes,
or
sir.
okay. Let me open a. I have to log in. Just a minute. Hold on. So you are talking about this angle, na? Here between this V2 and E2, right? What is the
Yes, sir.
how we are getting that angle? We are getting based on these two, and then only you will actually, if you have E2, then if you do this phasor sum, I mean this E2 minus I2 into Z2, that drop, that will give you your V2. So we can start drawing like this. That is why I have opened the whiteboard here. Let us draw it over here. So let this is your V2. Okay, this is your terminal voltage in the secondary, what you are getting, not the induced EMF. Okay, and this is your lagging current I2, which is the secondary current, right? Agree? Then what will be the what is the equation of your E2? E2 is basically V2 plus I2 into R2 plus J into I2 into X2, isn't it? Where R2 is the resistance for the secondary coil and X2 is the inductive reactance, right? So if that is there, then how can we write E2? I mean, how can we draw the phasor diagram for E2? This is V2, so that is V2, I2 and R2. This is in same phase with I2, and then J I2x2 means it is 90-degree leading, because this is the inductive voltage drop, so it will be leading your I2 by 90 degrees. So this is your J into I2 into x2. So once you have this, then you get this is your E2, right? This is your E2. So now you know what is the value of R2, what is the value of x2, then you can get the angle between these two, isn't it? So how can you get this? You can take this is theta, right? And then if you extend this, this is I2 R2 cos theta, isn't it? And this one will be, this is I2 R2 cos theta, and this will be how much? This angle, this is theta, means this is also theta, so it is 90 minus theta, so this is theta, that means this is 90 minus theta. So you get I2 R2 sine cos theta plus I2 x2 sine theta, that is equal to your this drop. So you know what is the value of V, yeah, you know what is the value of I2 x2 R2, and you know what is the value of E2, so you can get the angle between them. So this is one thing. Then once you get your E2, then as I told that E1 and E2 will be in phase, so E1 should be somewhere here, right? Agree? So if this is E1, then what we can draw, we can just extend this line and we can get this is as minus E1, right? Because polarity wise, minus E1 plus I1 R1 plus J into I1 X1 is equal to your V1 for the transformer, isn't it? So if we have found this, what is your E1, then next task is what? We can always write the phi, which is 90-degree lagging your minus E1 or 90-degree leading your E1. So this is your phi. So phi will have your magnetizing component Im, and then there is a core loss component which is in phase with this E1. So this is IC, which is very small. So this is your I0. That means your open circuit current. And whenever your secondary is open circuited, then this is the magnetizing component which you need. So now when you have your I2, actually I2 should be more and I0 should be less. So this we can extend and draw like this. Now what is the thing? We can find out I2 dash, which is 180-degree out of phase, just to balance the mmf produced by the secondary current, right? So this is your minus I2 dash, and that value will change depending on your N1 N2 ratio. So if this is I2 is I2 N2 equal to I2 dash N1, so your definitely your I2 dash will be more than I2. So in that way I have drawn here. This is your I2 dash. Now you should find the phasor sum of these two. So if I do that, complete the parallelogram, and this is your phasor sum, which is your I1. So now you have your I1. So I1 plus in phase, this is I1 into R1, and then this is your I1 J X1. So now if you add these two, you will get your V1, which is your supply voltage. Okay, so this is how you can draw the phasor diagram for the lagging PF load. Okay, so is it clear now? This is your
Yes.
this is Im, and this is your hysteresis angle, we can call it this angle. Anyway, this one, which is little less than 90-degree, this I0 and this E1, that relation. So this is true for lagging PF. And let me draw, actually in that figure it was drawn in the other way, like it was starting from in a vertical position, and V2 we have deliberately did this because we know this is what it's supposed to be. But whenever you do not know any, whenever you do have the values of R2 X2, and that means your equivalent circuit, then you can draw the way I have drawn. So this is also correct. Which one is easier for you, that you follow. Okay, you can follow this one. This is also correct. Then this is lagging PF. Let me draw it for the leading PF once. So procedure is same. Now it is for the leading PF load. So let us again start from V2. This is theta. So this is a leading PF. This is your V2. So V2 plus I2, then I2 R2 plus J into I2 X2. This is your E2, right? And E2 and E1 is in same phase. This is your minus E1. This is your phi, and accordingly we'll have it here Im, which is your magnetizing component of current, and this is the core loss component of current. And if you take the phasor sum of these two, you will get your I0. And if this is I2, then you will get your I dash somewhere here, I2 dash. This is just 180-degree out of phase, and magnitude will be multiplied because it is n2 by n1. And you can complete your parallelogram here. This is your I1. So now here minus E1 plus I1 into R1, then J into this is your V1. Okay, so you should draw it. If you draw it scale, then accordingly you will excuse me, you will get your result. Okay, that means what will be happening for this excuse me, what will be happening uh, here between E1 minus E1 and V1, those things will change depending on the value of the leading angle and all other parameters. Okay, as we do not know, I am just drawing it approximately. It can go even further here. R1 I1 R1 can go this side, and then maybe this one. In that way it will change. So I don't know the value, so approximately I'm drawing. And you also have to give the approximate sketch for this, because you won't be given the equivalent diagram, and from that you don't have to draw it. So this is what your phasor diagram, and this is how it looks like when you have PF leading PF load, and then here you have lagging PF load. Okay, so uh, with
Sir,
this
one thing I have to understand.
yes.
Yes, sir, in this slide only. Sir, why at secondary side it is V2 plus I2 Z2 equal to E2, and on primary side minus E1 plus I1 Z1 equal to V1? Why the sign is changing in one side and other side it is different equation? Sir, that I cannot understand.
Okay, so what is happening when we have, actually I think it is there in the slide. Let me go back. So here we are applying V1 here. First of all, here E2 and V2 within this here, this is E2 and V2. And whenever there is no load, E2 is equal to V2. But whenever, forget about the primary now, this part if you see, this is a EMF, source of EMF, which is E2. And this is having a polarity like this. And if you connect a load across it, So across the terminal, if there is an internal impedance Z, then how can you write this? If the load is having a V2 voltage, drop across load, if it is V2, if that is known to us, then E2 minus I2 into Z2 is equal to your V2. So E2 is the phasor sum of V2 plus I2 into Z2, or if Z2 is given as R2 plus JX2, then that we can substitute and we get the phasor sum of E2 as V2 plus I2 into R2. This is the phasor, this is the phasor, and then J into I2 into X2. Okay, so with this we get this. So here this indicates your E2 should be greater than your voltage across load, isn't it? Just like if you think of your non-ideal voltage source, I mean practical voltage source, it is E minus I into small r is equal to I into capital R, RL. Same way we have got this. So what happens? Your E should be always greater than your terminal voltage, which is V here, isn't it? Same way we have got this side. Is it clear up to this? And that is why we have drawn like this. If we just look here,
Yes, sir.
your V2,
Yes,
then
sir.
Z into I2 will give you your E2, right? This is V2, then drop I2 R2, then J into I2 X2 will give your E2. Is it okay?
Yes, sir.
This part is okay. Fine. Then let us go to this side. So whenever we are uh, in the primary part, when in the no load, actually what happens, if you are applying a voltage here, then what will happen? There will be a EMF induced in it. And why the EMF is induced? Because there is a alternating current through it, I1, isn't it? As I1 is is an alternating current, therefore there will be a flux linkage which is also alternating in nature, and then if you get the time derivative, then you will get your induced EMF. So as per Lenz law, what is the Lenz law, which is which indicates that E1 is equal to minus N1 d phi dt. So actually it should have a polarity which is trying to oppose your V1, which is actually trying to oppose the flow of current. So otherwise what will happen if it is uh, I mean aiding, then what to do? Then what will happen? It will there will be automatic generation of energy which is like violating the conservation of energy. So that's why you should have your E1 which is 180-degree out of phase with V1. Magnitude wise, it will be N1 into this. And whenever there is no leakage reactance and resistance, there is a no resistance in the coil and no leakage reactance, then magnitude wise, it is simply E1 plus uh, I1 R1, then whole square plus I1 X1 whole square root over of that, right? That is the magnitude. Opposing, that's why we have just given the minus. We either we can write it V1 is equal to E1, right, magnitude wise, but phase difference is 180-degree because E1 is equal to minus V1, right? So that's why we put it in this side. Either you can put it here, or if you have some leakage reactance and some resistance in the coil, then what is there in here, instead of that, instead of this diagram, if there is a load like this, if there is a inductive load, it is R1 plus J into X1, then of course across this what will be your V1? Your V1 will be shifted, it will be revised as V1 equal to, or rather V1 dash is equal to V1 minus I1 into R1 plus J into X1. That only the applied voltage here because of this drop. Okay, because of the drop across this impedance. So that's why we get V1 minus I1 Z1 is equal to your minus E1. So because of the Lenz's law, you are drawing it in the other side. Otherwise, it is magnitude wise, it is same. So that's why when we draw it, we draw like this. This is E1, this is minus E1, then this drop, then that will give you your V1. Not like it is, I mean V1 minus that, because equation is, here it is E2 equal to V2 plus I2 into Z2. And this is a phasor sum. E2 but here this is V1 is equal to E1 plus I1 into Z1, and this E1 is minus. Why? Because it is having a opposite polarity. So E1 is here, so we cannot draw it out from here onwards. So this is not correct, because they are out of phase to maintain the Lenz's law. Otherwise, will violate the principle of energy conversion. Okay,
Yes,
is it
sir.
is it okay?
Yes, sir.
Okay, fine. So now we'll go towards the equivalent circuit of a transformer. So whenever your transformer is, we have seen that whenever we connect a transformer with no load, I mean, the secondary is open circuited, then what is required? Only required is the magnetizing current, which can be represented by the equivalent circuit like this. It is in the ideal condition when there is no leakage reactance and resistance in the primary. Secondary it's also same. Only we have the current which is passing through the core, and for that you have the magnetizing component and the core loss component due to the iron core, all those things. So if you want to represent that through a circuit, so that equivalent circuit can be drawn like this, because whenever you connect the load in the secondary, then there will be another component. Then what happens, there will be some addition which is I2 dash. So that is why we can draw it in terms of parallel path. One parallel path is having one impedance which is Z2, Zm, whatever it is, and the other one due to the secondary circuit and load, all those things. So this is your Z2 plus ZL. So this is your I2, this is your IE or I0, and this is your total I1. Okay, so that's why we represent in terms of parallel path, but because of the magnetizing component, we have this, which is your R0 and X0, both will be, this is the magnetizing reactance and this resistance indicates the core loss component. So it is the uh, iron loss or core loss, whatever you want to mention, and this is the magnetizing reactance and this is the resistance due which related to the core loss part. So that we can draw like this two parallel branch, where one is the reactance, other is resistance, and we denote like this X0 and I0, where R0 is equal to V1 by IC. We have seen what is IC. If we go back here, this is your IC. In the ideal case, this is your IC and this is your IM and this is your I0. So I0 is basically the phasor sum of IM and IC. So that's why we have drawn the two parallel path. This is for IC and this is for IM. So IM is purely inductive, that is why it is 90° out of phase, 90° lagging, and IC is purely resistive, so it is in phase with V1. So we can therefore draw it like this is your V1, this is your R1, so you get your IC, and this is your X1, and here you get your IM, which is 90° lagging. So this is how we can represent the open circuit, I mean the situation when we have only we have the secondary open, so only magnetizing, we have only magnetizing current which is flowing through the core. Okay, so how can you get the value of R0 and X0? It is analytically you can get like this, which is R0 equal to V1 by IC and X0 equal to V1 by IM, and this IM and IC you can get like this, which is I0, that you can measure um, mm, with your ammeter. But anyway, practical thing, you cannot get like what is your phi 0, and for that you need to carry out, you should have the wattmeter reading and voltmeter reading as well. Then only you will be able to find out this. So V1 you have to measure, then you can measure I0 through ammeter, and then you should measure W, I mean wattmeter reading. So if that is known to us, then if wattmeter reading is known to us, then we can find out I, you know. So then you can find out the necessary calculation. We'll come back to that when I'll discuss the open circuit and short circuit test. But equivalent circuit we can draw like this when the secondary is open. Next we go to the equivalent circuit of the complete system, where it's look like this. This is your component, which is the I mean no load component, and this is the magnetized this path. Here still it is I2 dash, but after this ratio, this turns ratio, there is, this is your transformer. Actually here, this side, primary side, it is I2 dash, but in the secondary side it is I2 only. So that you can do only when you have this turn ratio like this. So you have to put like this. This is your E1 here, this is your E2 here, and now here it is R2 and X2. These are the leakage resistance and reactance, reactance and the resistance of the coil. This side also you have, in the primary side, this is your resistance of the coil and this is your leakage reactance. So this is how you can draw the equivalent circuit for the transformer as shown. And here you connect your load, which is ZL, and across ZL you have V2. So now if you look this circuit, you can understand why I was writing E2 equal to I2 into R2 plus J into I2 into X2, that is equal to your V2. Sorry, V2 plus this. I mean, if you apply your KVL here, you can able to find out, and same way. So V1 minus this minus E1 is equal to 0. Okay, so V1 minus this is actually your E1. So V1 is equal to E1 plus this. Okay, and same like here also, E2 minus this, that is equal to your V2. So it is equal to V2 plus this. Anyway, so now when we do not want to uh, put this, we can change the entire your this R2 and X2, which is in the secondary, we can bring in terms of primary, and we can remove this turn ratio, and we can draw like this. For that we need to do this exercise. So whenever the effect of circuit parameter should not be changed while transferring the parameter from one side, I mean from secondary to primary, or HV to LV, whatever you are trying to do. So one side to another side, when you want to change, their effect should not be changed. So when the resistance effect should not be changed, when I1 square R2 dash is equal to I2 square R2, right? So this is your secondary, which I want to refer in terms of primary. So for that, what we are trying to do, we are changing R2 in the primary side. So that's why we are writing as R2 dash. Just like the way the secondary current I2 we are changing in terms of I2 dash in the primary, in the same way we want to change R2 in the primary side. So if we want to do that, then we can write like this: your R2 dash equal to I2 square minus I1 by I1 square whole square, I2 square by I1 square into R2. So what is the relation between I2 and I1? I2 into is equal to I1 in 1. So your I2 by I1 will be equal to N1 by N2. Okay, so you can write it as either N1 by N2 square by R2, or you can get N2 by N1, which is equal to K. So you can write like this. Okay, so you, if you want to draw the equivalent circuit, now you can just remove this, and here directly you can write R2 dash, which is equal to R2 by K square, where K equal to N2 by N1. And in the same way, same thing happens for the this side also, for the x2 part also, because x2 part net your reactive power should remain same when you transfer from one side to other side. So I1 square x2 dash is equal to I2 square x2. This is your var, so that should remain same. So if that is the case, then again you get your x2 dash, which is equal to I2 square by I1 square. So you get x2 by k square, okay, as it is shown. So if R2 dash is like this, x2 dash is like this, you can get z2 dash in the same way, because it remains the same, because z2 is equal to z2 dash is equal to root over R2 dash square x2 dash square. So z2 by k square, okay. So then your overall thing you can write like this. And when you want to connect your load with the primary, then that also we should take care of. So if you have ZL, your ZL dash will be same as ZL by k square, like the way we are getting here. So that also you should change, and you get your overall circuit like this. So this is your complete circuit for the transformer, where it is the exact equivalent circuit referred to primary. So same thing if you want to do in the other side, then what will happen, your diagram will change. Let me draw it. So your diagram will change and it will look like this. And your this R1 will be R1 dash, which is R1 into k square, just the other way around. And this is x1 dash, which is k square into x1. Then R2 remains the same, x2 remains same, then your ZL remains same. There is no change. So this is the thing, equivalent circuit, when it is referred to secondary.
Sir, one thing.
Hmm.
Sir, what is the logic of uh, writing the core, connecting the core loss component and the magnetizing component impedances in parallel with the transformer? Why is
Okay.
it not in series? Like,
Hmm. If you just look the phasor diagram here, what you can see, this is your IM and this is your IC, which will give you your total I0, isn't it? So we can write as I0, which is equal to IM plus IC. So this is actually KCL, right? So when we can write in terms of KCL,
when it is parallelly connected.
so this is your Z1, Z2, say. We don't know what is this. So we can draw like this. This is your I0. Okay. And when nothing is there, only this is present, then this is how it should uh, behave. And then again, when
Okay,
you
sir.
connect your load, this will be your I2 dash. So I0 plus I2 dash is your I1 dash. So again another parallel path. So total three parallel path you are getting. One is for core component, another is for magnetizing component, and another is for your I2 dash, which is open. So it is not shown in the next slide, it is shown. So here you have, this is your 2 I2 and I2 dash and I0, and I0 you can further split in terms of IM and IC. So IM plus IC plus I2 dash is equal to your I1. So that's why we are drawing three parallel path. And as your IC is in phase with V1, so we are writing resistance here. And as your IM is purely inductive, so it is 90-degree out of phase. So we can write reactance XM there. Okay, because your phi and Im should be in phase, and phi will be 90-degree lagging your V1, right? So that's why you put XM there. Okay. If it is an ideal case, there should not be any IC. So directly we can put it as your this one XM, and your R1 you can omit. Like the way you have done your open circuit short circuit test, na? Same way. You can ignore the
Yes.
R1 part. Okay, so you can ignore this part. You can simply put this, and another is for your secondary thing, secondary your reactance. So here it is assumed that in the ideal case, when there is no leakage reactance and resistance in the coil, and no core loss component which is negligible, then if core loss component IC is very small, then your R0 will be very high. So if it is very high, we can assume it as a open circuit. Okay, so we can simply write it like this. This is your no load equivalent circuit. Okay, got it. And if you want to connect a load, like here in the ideal case, no drop here, no drop in the primary, no drop in the secondary, it is like that. This is your IM, and this is your secondary IL. So this side it will be it will be IL dash actually, and then that is equal to your I1. Okay.
Yes, sir.
Any other doubt to this? Okay, so whenever we want to express this, here it is exact equivalent circuit refer to primary. Up to this we have discussed. Then transferring primary side parameter to the secondary side, that also we can do R1 dash and R2 dash. Then you can either change V1, or this thing you can put this side like the way I have drawn. So that also you can do. Huh. Here what they have done, they have changed V1 also by V1 dash, so that you can have that same turn ratio adjustment. So here R1 dash equal to K square R1, X1 dash equal to K square X2, Z1 dash equal to K square Z1. This will remains the same, but these things will change, where your I1 dash will change, I0 dash will change, because you are changing all the current and EMF in the other side. Okay, so that's why these things got changed, and you can write like this by V dash. But what I feel, you can draw it like the way I have drawn, that is also acceptable. Okay, you can follow either this one. This one is easy to interpret. So if you can understand this, that is enough. Okay. Acha, now let's see what is their approximate equivalent circuit. Since no load current is only 1% of the full load current, the no load circuit can be neglected. Why? When we carry out the when we draw the equivalent circuit, approximate equivalent circuit, we ignore this. When we carry out two steps, like one is your short circuit test, another is open circuit test. When we carry out open circuit test, we can yeah, then there's very small percentage of current, of full load current, will be flowing through it, that we have seen, right? So whenever you carry out the short circuit test, that time you can ignore the parallel path, which is your magnetizing component, because that will contribute very less. So then if you measure your current, and if you have your voltage, then V by I will give you your net reactance and resistance or impedance of the coil. Okay, so that is what we do when we do the short circuit test and open circuit test. So with this, we just gradually move towards the transformer test. So performance of a transformer can be calculated on the basis of equivalent circuit, and for that we need to carry out the we need to find out the four main parameter. What are those? One is R01, and which is your core loss component. Then X0, sorry, no, this is not the core loss component, this is actually your resistance of the coil. X01 is your reactance of the coil, or leakage reactance. Magnetizing susceptance is B0, or the reactance X0, which is in the parallel path. So as it is in parallel, it can be written as B0, because that is what your susceptance, and conductance G0, which is resistance R0. So this is actually your parallel path. For that, this is R0 and this is your X0, and here you have 0 R01 and X01. The above constants can be easily determined by two, but here mind you that you are getting both. When you carry out the short circuit test, you are taking care of both R01 and uh, uh, X01, either in terms of primary or in terms of secondary. And for that, we carry out the open circuit test or no load test. So no load test is to find out your magnetizing susceptance and core loss conductance, or magnetizing reactance or core loss resistance, whatever you want to mention. And then short circuit test or impedance test also sometimes we call it, when we apply a voltage through auto transformer such that full load current will be flowing through the HV side. Okay. These tests are economical and convenient, and these tests furnish the result without actually loading the transformer. So to find out this test, you don't have to load it. What is loading? When you just add a load, then only your I2 current, I mean magnitude while will be there present. But if you do it with a short circuit test, then you can just keep on changing your voltage level. So you, that time you don't have to apply full voltage, only a small voltage if you give, then that will be sufficient enough to drive the rated current, right? So if we can do that, then we don't have to do it, we don't have to load the transformer with the actual load. Okay, so that we can apply very small voltage, and then with the that with the help of that we can get the values. So how, let us see it. So open circuit test or transformer secondary winding is open circuited, or we should call high voltage side will be open, huh? And primary winding we should call it LV, and we should call this HV. So you can see this is your low voltage side and this is your high voltage side. So your HV. So this is not the proper term secondary, because secondary can change. If you want to step down, then this concept will go just the other way around. So this is a relative word that better we should clearly mention why it is happening on the LV side and why it is happening on the HV side. Why are we could have solve it in the HV side as well. Now why we are not doing? We are not doing because to carry out in the high voltage side, we should use a higher rated auto transformer with which we should apply the full line voltage, which will be difficult, and your magnetizing current won't change, but to apply that voltage will be difficult for us. So that's why usually we conduct it on the, usually now always we conduct on the HV side when we carry out the open circuit test. To find what we are finding out, the no load loss or the core loss and the no load current, which is helpful to find out your G0 R0 and the X0. So how can we get it? What is your core loss? It is equal to what you are measuring from here. This is what you are measuring, which is your wattmeter reading, which is your voltmeter reading, and your ammeter reading. So your V by A will give you your impedance. I square R is equal to your W. So you can find out your R from here. And then if you want know your R, then from there you can find out your impedance. Okay. So let's see how here it is shown. The core loss component WC equal to V0 I0 cos phi, and cos phi equal to what? WOC by V0 I0. So you can get it as IC equal to I0 cos phi and I0 sin phi. And what is your I0? I0 is your ammeter reading. So in that way also you can calculate. Okay. So if you find out your IC and IM, then you can find out your, this is your uh, they have drawn it with I mean calculated it in terms of susceptance So this is your susceptance, which is I0 by V0. So what I have taken, this is Z, which is V0 by I0. They have done just the opposite. And then from here, they are finding out the different parameters. So your R0 we can find out by V0 by this I0 cos phi, and X0 you can find out as V0 by I mu, which is your magnetizing component. Okay, so this is how you can solve your parameter. You can calculate your R0, you can calculate your X0 based on these two readings. So one is WOC, another is V0, and another is I0, which we are getting from these two instruments. Okay, so this is your open circuit test. So I'm repeating. So WOC will get from this wattmeter reading, and you have your V0 I0. So you can find out what is your IC or core loss component and what is your magnetizing component. So if you have the wattmeter reading, if you know V0 I0, you can find out your cos theta. So if you know cos theta, then I0 cos theta is your IC. If you know sin theta, Im equal to I0 sin theta, sin phi it is written anyway. So if you know IC and Im, then your R0 will be what? It is V0 by IC, like the way we get it here. And V0 by Im will give you your X0. Okay. And if you want to find out the conductance and susceptance, then you can do it like that, just the other way around, inverse of this. Okay, so this way also you can find out your exciting conductance like this, which is your omega 0 c, I mean V square by R, actually V square by R0. So instead of writing V square by I0, it is written V square by G0. So any one you can approach out of these three approaches. Okay, which one is preferable to you? This is how you can solve the circuit parameter your with the open circuit test. So why we are not conducting the open circuit test on the LV side, HV side? I think it is clear to you, because we have to apply the rated voltage, and that will be difficult when we try to conduct the open circuit test on the HV side. Okay, but we do it on the LV side because it will be easier for us to apply the rated voltage in the LV side. Okay, so now let us go to the short circuit test. There we just do the other way around. We conduct the short circuit test on the HV side, and we short circuit the LV side. So why do we do that? Short circuit test secondary, again this is wrong term, this is LV are short circuited and the primary terminals are connected to a fairly low voltage. So if we apply some 10% of the rated voltage, even 6 to 10%, that will be sufficient to drive the rated current through this uh, thing. So we should gradually keep on increasing the variac, so that the rated current flowing through the HV side. So why we carry out in the HV side? Because for the fixed kVA transformer, if you do it on the HV side, only little voltage need to apply so that the rated current is flowing through the secondary. Okay, so that is why we do it on the high voltage side. The input voltage is adjusted until the current in the short circuited winding is equal to the rated value here. Okay, so we need to apply a very small voltage here in the this side, which is in the HV side, and then we shorted the low voltage side. Okay, usually conducted on the low voltage side. Usually conducted on the LV side means LV side we are shorting. Okay, and to find out the full load copper loss to determine the efficiency. Okay, so for that what we are doing here, this is the calculation. When it is in the short circuit mode, then this current will be much higher than that of the magnetizing component. So if your I0 is very less than I I2, then we can ignore the parallel path as if it is a very high resistance path. So we ignore this path and we have only this. So you have total, you have again the wattmeter reading, voltmeter reading, and ammeter reading. So from wattmeter reading and ammeter reading, you can find out your R01 and then if you divide VSC by ISC, then you will get the impedance. Then from there directly you will get your susceptance. Okay, so then once you are done, then you have both your R0 X0, which is your magnetizing and core loss component, and you have your R01 and X01. So this is how you can get your circuit parameter. So now if you, it depends on whether you have done which side you have done in the HV side you have connected. So accordingly, if you want to express the circuit parameters in the other side, I mean LV side, then accordingly you should adjust the scaling with the turns ratio. Or if you want to keep in this side, then that also you can do. It's up to you how which side you want to express your equivalent circuit. So I could not show the problems which will be useful. Maybe we need one more class in the upcoming week. Huh? Today I conclude. In the next week we can have one more class. So you have to adjust for that. Huh? I am not saying that I'll take in the scheduled time, because